Hello and welcome to another video. In this video we're going to be doing the last problem of the Biweekly Contest 121, and it's going to be count the number of powerful integers. And in the problem you're given three integers start, finish, and limit, and you are given a zero index string representing a positive integer. Positive integer is called powerful if it ends with s, otherwise s is a suffix of x, and each digit in x is at most limit. Return the total number of powerful integers in the range start to finish, and then they just tell you like what a suffix is and stuff. So it just has to end with it. So let's take a look. In this first example, start is 1 and finish is 6,000. Limit is 4 and s is 124. So they show you can have 124, 1124, 2124, 3124, 4124. And you can't have anything bigger. You can't have 5124 because every integer has to be 4 or less. And they tell you that there. So in the second one, s is 10 and limit is 6. So the integers in this range are 110 and 210, and 10 is less than 15, so that wouldn't work, so it's just these two. And then in the third one, limit is 4 and s is 3000, so there's nothing here because the smallest number is 3000. So let's just try to simplify this into some easy stuff. First of all, let's simplify the start and finish. So we want something in the range of start to finish. Notice that we're going to have some count here of integers that, like, let's say we wanted every integer that is less than or equal to, so we can write that down. So let's say we want numbers that are less than or equal to start, right? That'll be some number. Then we can actually get this range by just saying, let's just get all the numbers that are less than or equal to start, and let's get all the nums that are less than or equal to finish, right? And then just subtract them. So this would actually not be start, this would be start minus 1. So basically, if we have some range of like 500 to, let's say, 6,000, we can just say like, well, instead of doing that, let's get everything from here in some function from 0 to 6,000, and let's just subtract everything from 0 to 499, right? So that way we can kind of like eliminate this making sure it's in between them, and we can just do two separate calculations, right? We can just do some kind of calculation. Let's call it, we have a function. It will get everything that is start minus 1 or like from 0 to start minus 1. And then we will also get some that same function of, let's actually, right there. Okay. So this will be function of finish. So if we subtract these two, that will give us that range, right? So we simplified that. We got start and finish down to just one variable, like x or something. But now how do we do this? So we can't manually like check every number because this is 10 to the 15th, right? So we can't just like check every number in between these because this can be 10 to the 15th, so that's too slow. So we have to actually build these up digit by digit instead. And so this is something called digitdp, and I think I've done a few of these in the past, and I'll kind of explain how it is. And we're going to first solve an easier problem, and then we are going to solve the harder problem. So let's start with the easier problem. Let's just say we have some digits. Let's actually use an array that's indexed. So let's just say we have some number here, right? And let's say our number is, we want everything from 0 to this number, let's say. So let's just say this number is like 97629. So we want to say like how many numbers can we make that are this or smaller, and we're going to simplify this to not have the suffix part. We're just going to have the limit part. So we want every digit, let's say, to be less than, or let's say our limit here is 6. Let's actually change this 9 to a 5 because it's going to be relevant. So basically what we can do is we can just do like a DP problem where we have an index, right? So we'll be at some index, and we're going to say, so we take this number that we have, we can, and if you want to index it, the way I did it is you can just break it down into a string. So you take this number, you break it down into a string, and then you just traverse the number like digit by digit. Then basically, like for this digit, what are we allowed to have? Like what would be viable, right? Well, for this digit, we need our digit to be below the limit, but we also can't have anything above 5, right? So let's make another array down here. So let's say we choose, like, let's say one recursive case would be like we just choose a 5. So let's say we choose a 5, and then we recurse, and then we keep going. And okay, what about the second digit if our first digit was a 5? So our second digit has to be 6 or less, and it can't be bigger than 7, right? Like we can't pick. So if obviously, like let's say this limit didn't exist, even if the limit was like 9 here, it wouldn't matter. We could never pick like 8, right? Because this number would be bigger than this number. So we can pick some other digit. Let's say we pick like 5. Now notice that now that we have a difference here, right? Like these two digits are different. We can pick anything we want here, as long as it's obviously below the limit, and it wouldn't matter. Like let's say our limit once again was 9. Like we can pick a 9 here, and that would be totally fine, because the way numbers work, the way number comparison works, is once you pick a number that is smaller than some other number, everything else can be whatever, right? So if we go back, now that 5 is less than 7, all of these other digits can be 0 to 9. Now, assuming you don't have a limit, like right? Let's say your limit is maybe let's actually get rid of the limit for a second. So let's just say we have no limit at all. Let's just say we're trying to find all numbers. Like we're just trying to do. Obviously, you can just like return this number, but let's say we're trying to do some recursive solution. So because there is already a difference here, like we picked a smaller number, this can be 0 to 9, right? And then we can pick any one of those and then recurse into more states and more states and more states and so on. So that's kind of the idea, is if we picked a smaller digit at any point, we can now pick any digit. If we didn't do that, then we can't pick a digit greater than cur digit, right? So for example, if we went back and we chose a 7 here, well, now we can't pick like 8 or something because this will be bigger. So we basically need a variable to keep track of, like, did we do this operation? Did we pick a smaller digit? And so the way to do the digit DP is you have two variables for the state. So you will have an index, and then you will have this like, did I pick a smaller number? Picked smaller or something, right? Let's get rid of, let's move this. And so basically then our recursive case will be something like, you know, let's go back to the beginning. So let's say we're over here. We can pick any number from 0 to 5, right? Any number from 0 to 5 would be fine because these are all smaller or equal to. But if we pick 5, then this picked smaller will be false. We never pick something smaller. But if we pick anything else, then our picked smaller will be true. So if we pick like a 4 here, then we will recurse to index 1, and then we're just going to say we did pick something smaller. And we will just add up all of these recursive cases, right? So we will add up picking 0 to 5 and recurse appropriately, right? So we will just add up all of these like recursive DP cases. Now, if we want to include a limit, so let's go back and add the limit again. Let's say our limit is 6. So now it's very similar. Now we do still have this pick smaller, but now we can't. So for example, let's say we pick 4 here. We can never, whenever we do our loop for numbers we can never pick anything bigger than the limit. So we just add one more constraint saying like, before, since we did pick something smaller and this pick smaller is true, we could have had 0 to 9 here. But now that we have a limit, we can only have 0 to 6. And so that's the kind of thing, like if you can pick anything, so let's write that down. If you can pick anything, pick 0 to limit, right, this range. And if you have to pick numbers that are less than or equal to current value, because let's say we picked a 5 here. So if we picked a 5 here, we can't pick anything bigger than 7, but we also can't pick anything bigger than 6. So now our range is pick 0 to minimum of limit and current value, right? So if the limit is 6 and our current value is 7, then that means the value we could pick here would be 0 to 6. And whatever we pick, like let's say we pick 6, when we recurse, now we know we did pick a smaller number here. So now this can be anything starting here, but it has to be anything 0 to 6. So here we can pick anything 0 to 6. Let's say we pick 6. Here we can pick anything 0 to 6, and so on and so on and so on. And that's how you would do it, and you would basically just recurse, and then you would add up all of your recursive stuff. So now we have one more condition. Like this is how you do, and you can code this up, just get all of the numbers, you know, less than or equal to a number that have a digit limit. Like that's how you would do it. It would just be a DP function with this limit thing where you just have a state that says, did I pick something smaller before? If I did, I can pick anything as long as it's less than the limit or equal to. And if I didn't pick something smaller, then I have to pick something that is less than or equal to the limit and less than or equal to the current value. And then you just keep doing that and keep doing that and do that. So once this pick smaller is true once, it will be true all the way down, but you have to make it true once, and it will be true once as soon as you pick a number that is smaller than your current number. So that's how you do that. Now let's add the suffix. Like what if we actually have a suffix? So let's say our suffix here is, let's just say like 1, 2, 3, 4, 5. So basically at every digit we make for this recursive case, like all the logic is going to be the same, but we had to add a little bit more. So to add this suffix part, basically we have to add one more thing to the DP, and that's you have to check at every integer, am I in the suffix, right? So like, let's say let's just go back and start picking some numbers. So let's say we are here, and let's make this green actually. So let's use this, make it green just so it's different. So let's say we're here and we're picking some number. We basically have to check, is this in the suffix? So the suffix in this case is going to be the last 5 digits. So you can just do some kind of basic like figure out where you are and how many numbers you have left. So in my thing, I just calculated like how many digits am I from the end. So in this case, I would have like 1, 2, 3, 4, 5, 6, 10. So I'd say like here I have 10 digits left. And if my number digits that I have left is greater than the length of the suffix, then I'm not in the suffix. So if I'm not in the suffix, I just do what I did before, right? Where I just pick some random number. Let's say I just pick 5. Then let's keep going. Let's pick some random number. And remember, this is DP, so there's going to be a recursive case for all of these. So we basically have to come over here. We're still not in the suffix. We're 9 away. So let's just pick some random number. Which you can just pick like all of these for now. Let's say that our recursive case was this. 6, 2, 9. Let's just say this is what we ended up picking so far. Now we're over here. And so our state is we haven't picked anything smaller, right? So our pick smaller is false. We still have a limit, and now we're in the suffix. So now that we're in the suffix, there's going to be like a bunch of cases here as well. If we haven't picked anything smaller, if our suffix is greater than our value, like let's say our suffix here instead of 1, 2, 3, 4, 5 was like 6, 2, 3, 4, 5. Then this would never work, right? Because in this place, since we haven't picked anything smaller, we have to pick 5 or less. And if our suffix is greater, this is never going to work. So this is like one of the cases that you would just return 0 or something. So you would return 0. But let's go back to our original suffix. And they do tell us that the suffix is always like less than or equal to the limit, so you don't have to worry about that. But let's go back over here. So now our suffix is 1. So let's just check, is our suffix less than our value? Yes, it is. And our suffix is always less than the limit. So as long as our suffix is less than our value, it's a valid thing. So we have to pick a 1 here, right? We can't pick like anything we want. We have to pick a 1. So whatever stuff we had before, we're going to have a bunch of cases, but here we have to pick a 1. So we're going to pick a 1. And because we picked a 1 that is less than 5, now we are allowed to pick values that are less than 5. So we will turn on this like pick smaller thing. Then we will recurse over here. And we will say, okay, so we can pick something smaller than 4, but are we in the suffix? Yes, we are. Is the suffix value less than our current value? So actually, one more thing. So if we picked something smaller, remember, if we picked something smaller, now this can be anything, right? Because this is already smaller, like 1's already smaller than 5. Now that happened, now we don't have to, like this, now our suffix doesn't have to be less. Because now we can pick 0 to 9, like any value is fine here, and it also has to be little limit or less. So any value from 0 to 6 is fine. So we just have to check, like if any value is fine, if any value in the limit is fine, our suffix is always in the limit. So from here on in, it's going to be fine. So you can do like a short circuit. I don't think I did, and that's if you're in the suffix, and you can pick any number, then you can just return like 1 because this will always be valid, right? So you can just like your suffix, like this will be totally fine. Because all of these values are always going to be below limit, and all of these values here are in range of 0 to limit that we can pick, right? Because we already picked something smaller than the 5 here. So no matter what numbers we pick here, they will always be smaller than this whole thing. And so that's kind of like all the parts of it. So there's a lot, like I said, you have a couple checks. So the checks are have I picked a smaller number? If yes, then you can pick anything up to limit. And if no, then you can pick anything up to min of value and limit, or current value or limit. And then the other thing is, am I in the suffix? Am I in the suffix? If yes, and I can pick anything, you can just simplify it here to return 1 as like, basically the rest of your number has to be the suffix, and this will always work. And then if no, or if yes and I can pick anything, return 1. So there's actually 4 cases here. If yes and I have to pick value or less, check if suffix is less than or equal to value and recurse appropriately there. And now, what if you're not in the suffix no, then you just do like the other part that I did before. Just do normal operations without the suffix. And so that's all the parts to it. And then your base case is if you are out of bounds. So if you didn't return anything, if you are out of bounds, then you like found some valid word, so you will just return 1 there. You'll return 1, and then you'll have a bunch of cases where your stuff is invalid, so you can just return 0, right? Like if the suffix, like let's say the suffix number is greater than the value and you have to pick something that's less than the value, if the value is greater than the limit, like all these other things. I think actually if the value is greater than the limit, you won't be invalid, but yeah. So basically this is just like a big if-else things with like a ton of blocks, right? So you just have like a bunch of nested if-elses. But that's kind of like the code for it, essentially. You have to, for every number, just keep track. Did I pick something smaller? If I did, I can pick anything. Make sure it's all within the limit, and then make sure, are you in the suffix or not? If you're in the suffix, you have to pick numbers from the suffix. If not, you can pick anything. So let's look at the code. And it's kind of long. Scroll up. So originally, actually, it's kind of funny. So when I did this originally, it was super messy. And then this is a good use case for ChatGPT. Once you have a solution, you can ask it to reformat, and it said that it was too messy to reformat, like it couldn't follow the logic, so I actually had to like make it a little bit better, and then I had it reformatted again, and then it worked. So we have a cache, we have the length of the suffix, and then we have our DP function that will take the index and can use any digit, which just means, are we allowed to use any digit? Like, have we picked something smaller or not? And so if we're out of bounds, if we went through our whole number, then we just return 1, as in that's like a normal number. Then we have our cache case. And we want to take, so like I said, when I have a digit, like when I call this DP function, what I did was I actually took, so let's say I want every number that's less than or equal to like let's say this finish is like 5600 or something. I turn this into a string. So yeah, this would just be a string. You can make it, or I turn it into a string. You can make it like an array of numbers or something, but I turn it into a string because I want to be able to index every single digit. I think that was kind of easy. Like that, you could do some other stuff, but that's what I did. So then you want to get the current value. You check, are you in the suffix or not? So initially I say I'm not in the suffix, so I make it -1, and then the result that we're going to be returning. Then we just check, like I said, whatever number we're on, check how many numbers are left. So let's say here, this would give you like a 5 because there's 5 numbers left. So we check how many numbers are left, and then we check if that numbers left is less than or equal to the suffix, then we are in the suffix. And if we're in the suffix, we get the exact digit at the location we're in. So for example, if this is 5 digits left, that means we would take like the suffix length -5. So we get suffix at index 0, get this number 1, turn it into a integer. So then we'd get the suffix integer. Then, like I said, we have a bunch of cases. So if we can use any digit, and we're in the suffix, then this will basically always be true, because if we can't use any digit, we can use any digit from 0 to limit, and the suffix is always in the limit, so we can always recurse. Otherwise, if we're not in the suffix, let's just have a loop of using every digit from 0 to limit plus 1, because it's not inclusive. So let's say limit is 6, we'll try like 0, 1, 2, 3, 4, 5, 6. And we don't really need to pass the digit we use, so you can probably simplify this. You can probably just like result multiply this range times this function. But since we're caching, it doesn't really matter. Like if we call a function 10 times and it's O of 1, it doesn't really matter. But yeah, you can simplify this to make it a little bit faster if you wanted to. But because also this is only like loops like 10 times or something, it's basically irrelevant. Okay, so now we're in the other case, which is like the complicated case where we can't use any digit bigger than val. So once again, we check, are we in the suffix? So if we are in the suffix, then we have to use, so actually there's two cases if we're in the suffix. So if we're in the suffix and the suffix equals the current value, then we still can't use any digit in the future. So let's say, for example, our number is like 1, 2, 3, and we're in the suffix right away. So this is like our suffix, and this is our number. So if we're in the suffix right away and our digits are exactly the same, that means the recursive case, like we can't use any digit. For example, if the suffix has like a 4 here, this wouldn't work, right? So we're basically just checking, can we use any digit? If we can't use any digit and the suffix is the same as the current digit, we still can't use any digit. We have to use the digit that we have or smaller. Otherwise, the suffix is smaller than the current value, so we can use any digit later, which is, like I said, like if our number is like this, and we're in the suffix right away, let's say, and as soon as one digit of the suffix is smaller than one digit of the current value, then in the future this can be anything, right? So like this would be fine. And that's like the case that you have to think about. Like I said, I think you can simplify a little bit of these to not recurse as much, but because the index is only like 50, like these cases are very small, the index is only like 15, and use any digit is true or false. So this is like super fast regardless. So like you can simplify more, but basically the dimensions of the TP are like very, very small doing it this way, this digit TP. Okay. So yeah, if we have to use a suffix, we just check, is it the same value or is it anything else? And then we change our can use any digit appropriately. And if we don't have a suffix, then, so if we don't have a suffix and we can't use any value bigger than the value, we also can't use any value bigger than limit. So we just take the minimum of those and we loop from that. And then same thing, if the digit we pick is the current digit, then now we still have to use, then we still can't use any digit. And if the digit we pick is less than our current value, then we can pick any digit in the future. Then we just cache and return. Then I did some more things. I don't know if they're super necessary, but basically the idea is, let's say your suffix is bigger than like your left bound. So if your suffix is like 1, 2, 3, 4, but we want numbers between 0 and like 200 or whatever. So if the suffix is bigger than our left bound, then obviously we're not going to have any numbers there. So that's what I did here. So if the suffix is bigger than our left bound, we just say initialize it to 0, otherwise get the DP value of it. And then we clear the cache and we do the same thing. Same thing if the suffix is bigger than your finish number, like in the example that they had, it's just going to be 0. So basically, you take DP at the finish number, and then you take DP at start -1, and you subtract them, and that's going to give you the range between those. So that's what we do here. So yeah, like I said, if you go to, like for example, this one over here, you wouldn't even want a DP here because 3,000 is bigger than 1,000, so that would be like this part would be 0, and 3,000 is bigger than 2,000, so that part would be 0. So you know it's 0 right away without recursing. So that's kind of the idea of comparing and then doing something appropriately. Then, like I said, you basically just return whatever this finish value gives you when you put into DP, and whatever start -1 gives you when you put into DP. That's going to be the count in the range. And like I said, it's super fast because the constraints are very small, so we can go through that. So there are like a ton of if statements in here. Like I said, it's kind of a mess. So there's like, are we in the suffix? Can we use any digit? All these things. So there's like four total if statements. And figuring out exactly where we are in the suffix, what digit we are, like what all the bounds are is kind of a pain. So without comments, probably like 60 lines of code or something. But essentially, if we go back and look at our DP, So there are a bunch of if statements in the DP, but that's all one, right? Let's say there's like 8 if statements. That's still constant time. So the index, the biggest number we can have is 10 to the 15th, which so the index is only 15. So we can call this maybe like log base 10. So this would be like log base 10 of the biggest number we have, which I guess would be like finish or something. Right, and then suffix is the same thing. So suffix is basically around the same log of finish. So if finish, and this is a base 10 log, not a base 2 log. So like I said, if your number is 10 to the 15th, you will only have like 15 indices, which is nothing. And then your other condition is true or false. So basically what would happen here is it would be log of finish times 2, but because that's constant, we can get rid of that. So there's like only 30 states, which is like super tiny for like a hard problem. That's why it's super fast. And then, yeah, so this is going to be the time. And then we call this function twice. So it's just going to be like this times 2 or something, which is like super fast anyway. There's just like a ton of if statements, which add constant time to it. So, and space is going to be the same thing, log of finish. So once again, very small space. I think if we run it, I think it tells us space. Yeah. So I guess there aren't enough. But yeah, I don't know what's like the smallest thing that it is. Like if let's say we have like one space or something, but it's probably close to this. Anyway, yeah. So yeah, I think that's going to be all. And this one is kind of tough to code because there's a lot of DP and there's, like I said, there's a lot of like these if statements, like are we in suffix, are we not? Can we use the same number? Can we not? And so on. That's kind of a pain to code, but this digit DP thing does come up. This is just like a harder version of that problem because you have a bunch of like different things you have to follow, but they're not too hard to follow. It just basically adds like another if statement, so not too bad. And yeah, so hopefully you like this one, and if you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.